Yeah, thank you. Yeah, so I'm from the Theory of Hybrid Systems group at RWTH Aachen University, and we work on SMT solving, mostly non-linear arithmetic, but also linear arithmetic. And there we also use the simplex method, which is popular and successful for solving systems of linear constraints with weak relation symbols. But in SMT solving, we need also to handle strict inequalities, and this talk will be about this extension to strict inequalities. Okay, the simplex algorithm for lazy SMT solving was published first in 2006 by Dutertre and Demura, maybe also known as the general simplex method. And this method also contained support for strict inequalities. So the construction that is presented in this talk is already contained in this paper, but it was not proven there. In 2014, proof for this construction or this extension was given in the dissertation by Tim King, but this was really tailored specifically to this simplex method. And we present a more general construction, which is more general, applicable to also other algorithms. And also the proof of this construction is a constructive proof. And we hope also that this proof gives a bit more insight to the problem. So our contribution is the general formulation of this extension of the fundamental theorem of linear programming, and also the constructive proof. Okay, but apart from that, essentially, the things that are presented were also possible for our paper. Okay. So our problem is to solve linear real arithmetic, which are Boolean combinations of linear constraints, which are of the form, those are we have variables and coefficients, and the coefficients are from some field, and then this sum of or the linear combination of those variables is then compared by a relation symbol to some element from an ordered vector space, after assigning each variable to a value from also this ordered vector space. And the question is, does there exist such an assignment for x1 to xn such that the input formula is satisfied? Okay, so in SMT solving, usually, or lazy SMT solving, usually first a Boolean abstraction is computed of the input problem, and then a set solver solves this Boolean abstraction and passes possibly partial solutions to a theory solver, which are then sets of constraints. And then the theory solver needs to explain whether this selection of theory constraint is consistent with the underlying theory, and either he returns set or unsat plus an explanation in terms of a subset of the variables that he received. What is important to note here is that the set solver also might assign a Boolean variable to false to satisfy the Boolean abstraction, and thus also, even if we restrict the input problem to only contain weak constraints, then its negation is always a strict one. Yeah, so in SMT solving, we cannot get around this problem of dealing with weak constraints. We always need to, the theory solver always needs to be able to also satisfy strict constraints for this reason. Okay. So now we go a bit more formal. So what is the weak? So in the following, we first restrict to weak constraints. So less or equal, greater or equal to, and there we also note that For our proof, we can restrict to the less or equal case, as the other cases can be reduced to that case. Yeah, so this is what we will first look at, how we can solve weak linear constraints. We use an important result from linear programming. So what is a linear program? It's a maximization or minimization problem where we want to optimize a linear function with subject to some side conditions. And here we are only interested in the satisfiability of those side conditions, which we also denote by C. So this will be the system of linear constraints. Okay, and we are, the following, we'll also assume that the system C has full rank, because then the graphical interpretation is quite nice. So if such a system C is satisfiable, then the solution set is a polyhedron. And we call also the defining, the intersection points of all defining hyperplanes of those constraints in the system, we call them vertex candidates. And we know is that, well, if the solution set is non-empty, then there are these extreme points of this solution set, which are some intersection points of the defining hyperplanes. We call exactly those points vertices. And now we get the intuitive statement of the fundamental theorem of linear programming. So the part that we are interested in. So C is satisfiable if and only if it has a satisfying vertex candidate. Okay, and then there is the Simplex for SMT algorithm, and which simply makes use of the statement by starting with a solution or with a point, and it starts to and it does a local search now on those vertex candidates and improves the solution step by step until a satisfying solution is found. Well, and these improvements are done by so-called pivot operations. Okay. So this was a short introduction on the context of our construction. And now let us see how we can first prove the fundamental theorem of linear programming for weak constraints. For this, we need the notion of tight constraints. So a constraint C is called tight under an assignment if and only if, well, the solution lies on the defining hyperplane of this constraint, and or in other terms, well, P equals B is satisfied by alpha. And and we will also denote this constraint P equals B by C tilde in the following. Okay. Okay, so and for proving the direction of the theorem, that if the system C has a solution, then it has also a satisfying vertex candidate. For proving this, we start by any solution of C, and we make the solution, or we make constraint by constraint tight under the assignment, by simply moving the assignment to the boundaries of the solution set. And basically, this is the structure of how we could prove the fundamental theorem of linear programming. By proving that we can actually always find, that we can always move the assignment to such boundaries until we found a vertex candidate. Okay, for formalizing this, we need the notion of linear independence. So a set of linear combinations of variables. Here, Pi is called linearly independent. If and only if, well, all a linear combination or if a linear combination of those constraints, of those PIs is 0, then already the coefficients are already 0. And we extend this notion to constraints by simply saying that a set of constraints V is linearly independent if and only if their left-hand sides are linearly independent. And we call such a set V maximally linearly independent if V is linearly independent. And also we cannot extend V by a constraint C from C without making it linearly dependent. Okay. And we define all those maximal linearly independent subsets of a system of constraints C by MLI-C. Okay, now the fundamental theorem of linear programming restates the following. C is satisfiable if and only if there exists such a maximally linearly independent subset V of C, such that there exists an assignment that lies on the boundary of such of the hyperplanes of V, so the intersection point of the defining hyperplanes of the constraints in V. In other terms, alpha is a vertex candidate of C. Okay. So this is the case for grid relations, where we always look for solutions on, in the vertices of such a system. But how does that work for strict relations, where the boundaries of the solution set are actually excluded from the solution set? Then we need to, what we now want to do in the following is we want to find a notion for the solutions that lie in the solution set but are arbitrarily close to a vertex of the relaxed version of the system. Okay, so how do we do that? We do that by first eliminating strict constraints by introducing a new variable epsilon, and we will now assume that we assign to epsilon a value that is small enough, but above 0. Okay, so this will be the interpretation of our variable, and by doing this transformation, of a two-dimensional example, well, then obviously we introduce a new dimension, and the transform system now looks like a tent. And the floor of the tent is the original system, but then there is like this area below the constraint and above this floor, which is then the solution set of the transformed system. Okay, and what is easy to see is that C is satisfiable if and only if there exists a solution for the transformed system with a positive value for epsilon. Okay, so the one direction is quite easy. So if there is a solution with a positive epsilon for the transformed system, then we can simply project out epsilon and find a solution in the original system. So once we have such a solution, and this we will see later how we find such a solution, then we are basically done. The more challenging direction is to show that when the original system is satisfiable, then we also find a solution for the transformed system with a positive epsilon. And for proving this direction, which will also be the more tricky part of this of our proof and focus of this presentation, we first observe that given a point in the original system, we can, in the transform system, we can move this solution up into this tent here, and we can move it up until we hit the tent's roof. We know that every point between the tent's roof and the original point will all of those points here are solutions of the transform system. Okay. And what we now want to do in the following, we want to get an analogous notion or a statement as in the fundamental theorem of linear programming. We want to get now solutions that are close to a vertex of the original system. So what we do is now we apply the fundamental theorem of linear programming to this statement that we have just seen. And what we now get is that we can we can basically move now the solution along along a phase, a facet of the solution set, and we know that the projection always goes now arbitrarily close to a vertex of the original system. So this will be our goal, to prove now. In this example, this is quite simple, but we will see what the trick part is in another example. So in a one-dimensional one. Okay, so we have here only one variable, and after the transformation, well, it looks like this. And what we are interested in is really getting this red point here, such that the projection gets arbitrarily close to a vertex of the original system. Okay, and how do we construct that? How can we actually move this red point arbitrarily close to the blue point here? For this, we start with, again, we assume that the transform system is satisfiable. So we take any point alpha. And what we now know from the previous slide is that any point between epsilon equals 0 and this point is a solution of the transform system. Okay. And then we apply the fundamental theorem of linear programming to move all those points to the boundary of the solution set. And now we know that we can move this red point here along those boundaries. This still is quite unhandy. So what we really want to have is we want to move this red point along one defining hyperplane in this example. Yeah? So we need to prove that actually we can move this G here, this upper bound G, small enough such that the boundary of the solution set of the defining hyperplanes of this boundary we can choose them constant such that we can move along those defining hyperplanes to get our point arbitrarily close to a vertex of the original system. And after we have done that, we get this intermediate result here, which looks a bit unhandy as it still contains the quantifier alternations, which we want to get rid of in the following. And we do this by now interpreting this variable epsilon as an infinitesimally small value. We define this as a positive value, which is smaller than any other value from our vector space U. And by introducing this semantic, this gets basically a extension of this vector space, which and this extended vector space is now called U epsilon. And basically, and then we get a lexicographic ordering on this vector space and also additional multiplication naturally. And this this semantic of epsilon is nothing special. It's I think well known. I think it's called hyper real numbers or something like that. It's the same semantic for the epsilon here, but we only restrict to yeah, a vector space here. Okay. And finally, by using this semantic, we get a statement that is now similar to the original formulation of the fundamental theorem of linear programming. Well, what the differences are? Well, now we interpret our relaxed version, the transformed version of the system C as with this special semantics for epsilon, and that's basically it. And then we know that the C is satisfiable if and only if there exists a maximally linearly subset V of this transformed system, yeah, such that there exists a satisfying vertex candidate for this transformed system with a special semantics for epsilon, which is similar to the original formulation, as you can see. And this transformation, it seems intuitive, it seems obvious, but it is not when looking on it in detail, which can be confusing. If you see by discussing this example here, where we have an overdetermined vertex, so we could choose C1, C2, C1, C3, and C2 and C3 as the constraints inducing yeah, the vertex or the vertex candidate of the depicted system. And by making one of those constraints strict, we see that in the transformed system, the special semantics for epsilon, we now get two vertices in this transformation. Okay, and by making also the other constraints strict, also those also can collapse to one vertex again, but this is not guaranteed. What also can happen is if we, for instance, scale C1 by a factor before applying the transformation, before eliminating the strict inequality, this does not change the solution set of the original system, but it does change the solution set in its transformation. As you can see here, now we have instead of one vertex candidate, 3 vertex candidates, where 2 of them are actual vertices in the transformation, but 1 is not. Yeah, so we have really some combinatorial overhead here that is introduced by our construction. Yeah, so this fact here can be a bit confusing and counterintuitive. Another thing that I did not talk about so far is how to handle the not equal constraints. And for now, we simply interpret this, or we are happy with checking, well, the system C is satisfiable with interpreting this not equal as a strictly less constraint and interpreting it with a strictly greater relation. So this way we check actually for every not equal constraint, we check 2 systems for satisfiability in worst case, when we cannot avoid this. Okay, and this also, as you can see, introduces an exponential overhead. Okay, so to conclude, what we saw is a drop-in extension for the fundamental theorem of linear programming, which allows us also to handle strict constraints with all algorithms that rely on this theorem, especially also applicable to other algorithms than Simplex, which was also the case in my master thesis, where we worked on an adaptation of the Simplex algorithm, where we wanted to move the combinatorial part of the Simplex into the set solver and then only solve yeah, a selection. But I wanted to check if the system is satisfied at a certain vertex candidate in the theory solver then. So this was an adaptation, and for this adaptation of the simplex method, we needed the formulation presented in this talk. We also know that other approaches for handling strict inequalities require a deeper modification of the algorithms. What would be interesting, or also in the future, how if alternative approaches can avoid this combinatorial overhead, which I mentioned, and also avoid the blow up that is caused by those not equal constraints. So there we have some ideas. We are also working on some other linear algorithms for solving linear arithmetic. We will also use the adaptation presented here. And there we have also ideas to attack, especially the second issue here. Yeah. And also what we are interested in is when we were researching solutions for handling strict inequalities, whether there are also applications for this extension outside SMT solving. Okay, thank you for listening, and I'm open for questions.
Thanks very much. So all this is in the context of solving inequalities over the reals. How much would this help in looking at mixed integer real programming?
Yeah, so I think it's so usually when you solve integer problems, you always use some other procedure that uses simplex. So the simplex always solves a relaxed version, right? And so of course you can use this construction here in the simplex method. So I think in this way, when using simplex as a sub-procedure, solving some relaxed version, then you can apply this transformation. I don't know if this transformation can help with, yeah, I think in this sense you can use that, but I'm not aware of any deeper connections.
Okay, thanks. Yes, it's just there's obviously some connection there, but yes. We've got time for a couple more questions.